this is a second example problem using the Biot-Savart law to find the magnetic field for some symmetric situation. In this question, we're going to find the magnetic field B at a point along the axis of a charged spinning disk. And so that means we're going to come up some distance d to some point there, and we're going to ask what is the magnetic field at that point. Now to do this, we're going to use the result that we have before, and that's the magnetic field for a current loop, for a circular current loop. And so this is the result we're going to use. That's what we did in the last example. Now the way we're going to form this is we're going to say that this spinning disk is made up of a bunch of current loops, and the disk will be, or this distance here we're going to call dr, and the radius here we're going to call little r. And what we're going to say is that we're going to say that the total magnetic field at the point D is the sum of the magnetic field from each little disk. And how do we write that out? Well, we just use the superposition principle. And so obviously here I have dr, I have a sum, I'm going to want to do an integral here. So integral dB is going to be B. So our total magnetic field is going to be the integral of each little part of the magnetic field from each disk. And so now I have to write down what each part of the magnetic field is. So dB, and this is where I'm going to use this previous result. And so taking this here, we are going to write down, this is mu naught. Now we'll leave some room here for a moment and fill that in. A is the radius of the spinning disk. For us, that's actually little r, so this will be little r squared divided by 2 little r squared plus d squared to the 3/2 power. Now we have to think about what this current is. Now we know, or we have learned already, that the current density J is equal to rho times V. Well, for us we have a flat thing, so that's going to say that instead of the volume current density and the volume charge density, we're going to say that the surface current density K, so doink doink, K is going to be equal to sigma naught, that's our surface charge, times V. But V in this case is going to be omega times R. And so we're going to have that the magnitude of K, at least, is sigma naught omega R. Now to get current from a surface current, we have to multiply it by the width through which it flows, but that's just dr. And so finally for us, we're going to be able to make the statement that the I that we're looking at is sigma naught omega r dr. So I'm going to copy that up right here, sigma naught omega r dr. And then I'm going to rewrite my magnetic field. My magnetic field is now written by this integral. I'm going to pull some stuff out front. Mu naught omega sigma naught divided by 2. Then integral from 0 to a of, we're going to get r cubed dr divided by r squared plus d squared to the 3/2 power. And so we're pretty much at this point done with the physics. I've said this many times, this is a physics class, not a math class. It doesn't matter how you do these integrals. And so I looked it up on Mathematica, or plugged it into Mathematica. And so the result of this, then, if I take my equation down here, is this is mu naught omega sigma naught over 2 times a squared plus 2d squared over the square root of a squared plus d squared minus 2d. And there you go. That is the magnetic field due to a spinning charged disk.